人工智能开发专家，他也是谷歌 GDE Kshitiz Rimal，然后他会和大家一起分享今天的这个这个报告，主要是关于那个TF Agent 的这个使用的一个内容。那么现在呢，我要有请那个大连 TFUG 的那个小蔡给大家做一下介绍。哎，小蔡。
Hello，这边是TFUG 大连的蔡永基。就是我们的这次演讲呢，今天虽然是英文的，但是就是 Lion 然后做了一些翻译，然后我们也可以就是说有中文的还有英文的，所以也没有那么难。然后抽奖的形式呢，就是希望是谁先发问谁提问题，然后谁就会优先得到奖品，然后其次是剩下的会有抽奖的形式来进行。
好的，那这样好，成都这边我们的主要的主持人是那个我 Kshitiz，然后还有旭东，我们三个是那个 TFUG 最早的创始人嘛，成都的，然后大连主要是小蔡。如果大家在这个过程中有什么问题，可以给我们提出来。然后先是那个Kshitiz 他会分享他的 report，然后在这个 report 的过程中，所有的大体的这个我们都已经做了翻译。在这个他演讲的过程中，我们是不会对他的那个内容进行翻译，但是后面如果大家提问的话，我们会尝试着把大家的问题翻译成英文，然后告诉他，让大家做一个互动。在这个过程，后面的过程中，我们会开那个语音，大家就可以积极的来参与其中哈，和那个Kshitiz 来做这个交流。那我们现在准备开始哈，Kshitiz 会做报告。Kshitiz，we have talked about your report and yourself. So now you can introduce yourself. After that, you beginning your presentation. Okay.
Okay, great. Thank you so much. Let me share my screen and share my presentation with you. So, can you see my screen?
Yes.
Okay.
Yes.
Okay, great. Thank you. Okay. So the session today that we're going to talk is called Deep Reinforcement Learning with TF Agents. And thank you, Leon, thank you, Guy, and everyone from TFUG Group for this amazing translation. I don't know Chinese, but it looks amazing, and thank you so much. I hope this will be very insightful, entertaining, and you will enjoy this session. So before I begin, let me share brief information about myself. I am Google Developer Expert on Machine Learning from Nepal, and I'm also head of research at this organization called AI for Development, which is a not-for-profit research organization in Nepal. And we do deep learning projects for our community that can help our community, things like AI for accessibility, AI for disaster relief and response, and so forth. And if you like to get in touch with me or contact me, here are my contact information, my email address, my LinkedIn handle, and my Twitter handle. Okay, so let's begin with our session. So this is the brief overview of our session. First, we'll talk briefly about supervised learning and the difference between supervised learning and reinforcement learning. Then we'll talk about how we can get started with this reinforcement learning, or specifically deep reinforcement learning using TF agents, a framework to do just that task using this in this TensorFlow ecosystem. And then we'll go through this step-by-step procedure to train an agent using this TF agent framework. And then at the last, we visualize the result and visualize the evaluation and see how well our agent will perform after the training. So let's talk about supervised versus reinforcement learning. So when we talk about supervised learning, we're basically talking about machine learning or deep learning. And they are called supervised learning because whenever we need to train a deep learning model or machine learning model, on top of this training data, we also provide labels to this data. Meaning, so if you're trying to build an image classifier, you not only just provide image, but you also provide associated label for each image, so that our deep learning model can learn from these labels and try to perform image classification on new data. So that's why they are supervised, because we are supervising the learning algorithm by providing a true label to true label to all these features like image or text or whatever. And when we talk about supervised learning and deep learning, basically these are the tasks that we can expect nowadays, and they include image classification, object detection, and gesture recognition, pose estimation, and so forth. And they are all part of supervised learning, because every training procedure here has an image or pose data and their associated label. So that's why they are supervised learning. But there are some challenges with this approach. They are really great on training these models with supervised learning, but the approach itself for this supervised learning is a bit challenging. And we'll talk about that in a while. So all these networks, this image classification network, this object detection models, they are all built using framework like TensorFlow. And to get started, or to give you a brief idea of how we can build a simple neural network or deep learning model using TensorFlow 2.x, this is a small, hello world kind of example using TensorFlow 2.x, the latest version of TensorFlow, to build a deep learning model. So as you can see, in few lines of code, here we are creating a deep learning architecture. Here we are training our this newly created deep learning architecture using our own data and their associated label, and then we can evaluate the model using some test data and their label. So with this few line of code, we can easily create TensorFlow deep learning model. And so we know that this is very easy with deep learning, and it's very simple to create this kind of a neural network, and not just a simple neural network like this, but we can also create very amazing performing, generative models or object detection model or high performing other kind of model using TensorFlow 2.x. Now, this talk is basically about reinforcement learning. So let's talk about some of the challenges that I briefly mentioned earlier associated with supervised learning. And the challenge lies itself in the approach, how we train the model. So in supervised learning, we require a label data set, and that is the biggest concern for our for the multiple of tasks associated with learning algorithm. And because every problem that we want to solve using an artificial intelligence might not frame properly into this context of features and label, and they can be problem associated with decision making or simulation or other kind of a thing, and we cannot always map our problems that we want to solve using the AI, using this label dataset and their associated features. And sometimes it's very hard to create label dataset as well. And another thing is that, like I said, it's not ideal for every learning problem, and that kind of learning problem can be decision making. So right now we have seen the example of image classification or object detection, but what if we want our AI to make a decision on certain scenario, and that way, and we might not have a proper label associated with every scenario and how agents should perform, and the label itself limits the learning capability of our agent, of our artificial intelligence algorithm. So it's not ideal to have this label and dataset scenario to solve every kind of AI task, and that's why we need reinforcement learning. So this definition is taken from Wikipedia, and it says that reinforcement learning is an area of machine learning concerned with how software agents ought to take action in an environment in order to maximize the notion of cumulative reward. And so what it means is that we create an AI algorithm, an agent that will try to solve a certain task without a label, and the only objective for this agent or this AI is to solve the task which will have at the end the maximum reward point. So this is how we train a AI algorithm using reinforcement learning, so that the AI algorithm, the agent that will try to learn by taking an actions or making a decision that will end in having a maximum reward to itself. And this is how we train the reinforcement learning algorithm. Now, to understand this reinforcement learning or this deep reinforcement learning, which is this deep learning and reinforcement learning, we will try to, set an example here. And for the sake of explanation and for the sake of learning the simple rule behind reinforcement learning, I have devised an example which is called a game. It's a hypothetical game that we'll try to train using reinforcement learning. And this game is called Dog in a Park. And it's a very simple, interesting kind of game where dog try to solve a maze kind of environment using reinforcement learning. And to give you a disclaimer, this session is a very beginner-friendly session, and and this is particularly useful for those who are very new to reinforcement learning, and so far, all these materials on the internet using reinforcement learning and deep reinforcement learning, they try to explain to these concepts using very high level and technical jargon, which might not be very easy or easy to learn for beginners. And that's why I wanted to take this time to explain reinforcement learning with simple examples and how we can intuitively understand what is going on using reinforcement learning. And in this session, we're trying to debug that, explore that reinforcement learning very basic concepts, and try to train an agent, an AI algorithm using reinforcement learning, using this framework called TF-Agent, using this example of Dog in a Park game. So the game is very simple. We have a dog who is in a section of a park, and this area is a park. This area is a section of a park where our dog is at the initial position, and it's a very interesting kind of game that I'll try to explain to you. So the task of the dog is that the dog should not be in this park. It's a access denied kind of area for a park, and since our dog is somewhere that he should not be, so this dog is called Kiko. I have named the dog as Kiko, and the player, the dog Kiko, it should not be in this section of a park. And every instant of a time he spend in this park, it's very risky for him, so he wants to get out of the park. But at the same time, this dog Kiko is also very greedy dog, and he wants to collect as much bone as possible when he get out of the park. And right now the dog is at the initial position of the park, and he wants to get to this end position, this X position, which is the end of the park. And when he reaches that position, the game will be complete, and the Kiko has won, and things like that. And as the dog is very greedy, he also wants to get to this end position of the park, but at the same time collect as much as bone as he can while traveling all this section of the park. But here is the catch: there are some robots in that park. So if Kiko accidentally step onto the position of the park where there is a robot, then he is out of the game. The game is over, and there will be penalty for him. And if he step onto the position where there is a bone, then he gets a reward. That is, he gets the bone. So the task of this player is to get to the end of this park, this X park, by avoiding all the robots and collecting as much bone as possible. This is a very simple game environment, and we'll try to train our dog, our agent, our player here using reinforcement learning to get to this position using as much bone, collecting as much bone as possible, and avoiding all these robots in the park. So the player of the game, Kiko here, is an agent. It is what we call in the term of reinforcement learning. So an agent is a player who performs in an environment. And the section of the park here is called an environment. In an environment, it exists everything, like the dog itself, the robot, the bone, the end position. Every little instance of this park is an environment. So what it does is that the agent performs certain action on the environment, meaning the agent, which is the dog, moves in the environment. Either he can move left, right, top, or down to get to the end position of the part. So this moving, this moving operation is called action. So the agent, the dog, will perform action on the environment. So here is some explanation of state, step, action, and observation. These are all the technical terms that are used in reinforcement learning. So I'll try to break it down to you so that you can get familiar with all this, terminologies. So a step is a particular action that the agent will perform on the environment. In this case, at the initial part where game just open up, the agent, the player, is at the initial position of the game. And when the agent moves to the right, to this position, then it will perform one step. And to perform this, to go to this one step, to perform this one step, he has to perform a action. So in one step, the agent, the player, will only take one action. And when the agent perform a step or action in this environment, he will change the state of the game from this initial state to this one, where dog has now a new position. So every time our player, our Kiko, takes certain action in this park, in this environment, the state changes, either from this position to this position, and so on. So every action leads to new state. And observation is basically whatever this dog can observe from this environment. So this is a very simple environment. So in this case, the dog can observe everything that is happening in the environment. That is, whenever in this, the dog, whatever the position he is in, he knows where the bones are, where the robots are located, and where the end position, end location of the environment is located. So in every state, the dog knows what is happening in an environment. And that observation, that knowing of where the dog is he himself located in the park and what is happening in the environment, is called observation. And that is not always the case for complex environment, like sometimes in the case of physics simulation or a self-driving car or other kind of complex environment. The agent, the player who is playing the game, might not get all the idea of where all the enemies are located in the game or where the end position are. So that's why sometimes, or many of the time, the observation is little bit less information than the actual environment or the state of the game. So, but this is a very simple game example, and here the state, the observation, is the same as the state of the environment. So the dog knows everything about the environment in every action, when every action he takes. So to break it down, to recap a little bit here, so we have a game where the rule of the game is to get this dog, our learning algorithm, our agent, which is the dog, to get to this end position in time as fast as possible. And while doing so, he needs to avoid all the robots and collect all the bones, how much he can, And the agent, the player, is the agent of this game, which is the learning algorithm that we're going to use. And the environment here is the park, the section of the park the dog is in. And every time the dog performs certain action, he changes the state of the game from certain previous state to the new one. And he gets to observe what the new state is by observation. So he can observe whatever happened when he takes certain action, and he gets to know whatever happens when he takes certain action to the environment, and that is the observation. And there is a concept of action and reward, and like I mentioned in earlier slide, reinforcement learning basically deals with training the agent, the algorithm, by the terms of reward. So what does that mean? So it means that whenever an agent performs certain action, like in this case, when agent perform right from this initial position to this one, the agent gets nothing, and he gets penalty or negative reward of minus 0.3, because the environment allows, the rule of the environment is that the player needs to get out of the environment, get to this end position as soon as possible. So every time he perform any action, he will get certain negative reward because he needs to get to this point as soon as possible. But when the agent get to the position where there is a bone, then he gets a reward of 1. That is, he will not get penalty, he will get a reward of 1. That means we are allowing our agent to learn that he needs to collect as much bone as possible. And when the agent, while performing all this movement and collecting bone, when he gets to this end position, he will get total reward, the maximum reward of 10, meaning that the maximum reward the agent can get is 10. That is, he needs to get to, more than anything, he needs to get to the end position of this game. But at the same time, if he gets to this bone location, he also get a reward of 1, meaning this is also like a sub task for our agent to collect as much bone as possible. But when he if he accidentally step to this robot position or into empty position, then he should get a penalty, meaning that he should not be like stepping onto this robot position, and he should avoid making less beneficial steps and get to the end position as soon as possible. So basically, with the terms of reward and penalty is basically negative reward. So with the help of reward and penalty, what we are trying to say to this agent, this dog, is that, okay, avoid stepping on to the robot position and get to the end position as soon as possible, and if you can, get as much bone as possible. So with the terms of reward, positive point, we are reinforcing our agent to get to the end position, and at the same time, with the help of negative reward, then we are trying to train our agent, okay, avoid this step. So whenever the agent steps to this robot position, he gets out of the game with a negative reward, and that gives him like, okay, oh, I should not do that, I should not perform that step again. So that is how we are training our agent, by the terms of action and reward. Agent performs certain action, and if the action is beneficial, then he gets the reward. So to break it down, this is what happening. Sorry about that. So so essentially what is happening is that the agent, the dog, is making all this decision where to go next in this, where to go next to this environment by using a deep neural network. And in this case, this deep neural network is called deep Q network. And what is happening essentially here is that, okay, this deep neural network will act as a brain to our agent, our dog, and it will help our agent to make a right action to get the maximum reward when the game ends. So all this deep neural network is doing is that it is taking state of the environment where the dog is now currently positioned, and giving idea to the agent, okay, you should take left or top or right or bottom action, so that at the end of the game he will get the maximum reward. So basically, deep neural network is acting like the brain to this reinforcement agent, which is our dog, and it is helping our dog to make all the right position, all the right action given the current state of the game. And this kind of neural network is called deep Q network, and this Q here basically stands for quality, and what it essentially means is that given every state of the game, the deep neural will try to predict an action that will maximize the cumulative reward at the end of the game. So this deep neural network will always give prediction of the action that will lead to the maximum reward this deep neural, agent, our reinforcement learning agent, will gather throughout the game. So this is all happening here. The agent, which is whole dog, is taking an action with the help of a neural network, and when the agent performs certain action on our environment, which is the park, he will observe the new state after performing the action, and he will also get reward from the environment, giving whether he has performed good action or bad action. And that using that analogy, using that method, it will train the neural network associated with that agent. So this is the overview of the game, and this is the terminology that is basically used while creating this deep neural network or this deep reinforcement learning algorithm using this analogy. So let's get started with TF agent. So TF agent is a framework that allows us to train this deep Q network, this agent, this dog in our custom environment, which is dog in a park. So to break it down, this is the high-level diagram of TF agent. So TF agent is a part of TensorFlow ecosystem, meaning it uses many functionalities and the modules of TensorFlow itself to train this deep reinforcement learning agent. And as you can see from this diagram, the agent, the dog, is situated here. And the policy model is basically this deep Q network that is acting like a brain to this our agent. So the task of this policy network is to give our agent what he should perform. So basically in this diagram, what is happening is that our agent is performing as per the policy given by our deep Q network. And while performing that policy, this action, he will perform that on our environment here. And while performing that action in our environment, he will observe all this new state while performing this task and collect all the reward or penalty that he will receive while performing this action. And these are all collected as a part of trajectory. And this trajectory is nothing but a collection of state from previous state to the next one in a concise representative manner. And the trajectory, as the name suggests, is like a representation of previous state and the next state with its associated action and reward. And while performing this action using this policy on the environment, he will collect all these states that is happening. And all these states in the form of trajectory are stored in a memory called replay buffer. And from this memory, the agent will be again trained to perform better in the next iteration. So here what is happening is that the agent is getting all this previous action, the agent has performed all this previous action and state the agent has performed using this memory, this replay buffer, and he will try to train from all this previous action he has taken and from all this previous trajectory. And while training from this previous action, he is also allowing to explore himself to perform new action, so that in the next iteration and so forth, he will collect new trajectory and perform better as he trained. So I will break it down all these submodules one by one. So just to give you an idea, this is the high-level architecture of the agent and how we can train our agent using TF agent. So the first step to create a TF agent to train our this dog reinforcement learning agent using TF agent is create an environment for our game. And this means like creating the rules of our game, the environment where the agent will perform, and so forth. And to do that, first thing we need to do is create a class, a Python class that will act as a game logic to our environment. So this is a simple Python class where we will hold every information and rule of our game. So let's call it dog adventure class, and here we'll store the environment details, the action, the agent can perform, and the response when performing certain action. So first thing first, let's create this class called dog adventure. This will act as a game logic. This will act as a logic to our game. And so here you can understand is that this game, this environment is a 6x6 grid essentially. But to make matter very simple, what I have done here is that I have created this environment in the form of one-dimensional vector. So instead of making a 2D of 6x6 array, I have basically created a one-dimensional array with 36 positions. That is basically 6x6 array. But using this one-dimensional approach, the computation will be much simpler than in the 2D array. So this I have just initialized a game state with all the position to be 0, and 0 means empty position. And with this line of code, what we are doing is that we are creating a one-dimensional array which will act as an environment or state of our game, and basically we will fill every position right now with empty position. Then after that, we will fill the position where we want to locate our robots in the environment. And basically I'm providing the index where the robots will need to be placed in this game environment. And if you count, you will see that the robots are placed in 6th position, 10th position, 14th position, 25th, and 33, like that. And similarly, we also provide position where we want to locate the bones in the environment. These are all the positions where the bones will be located in our environment. So, and then what we are going to do is that basically 0 means empty spaces where our dog can move freely, and we are basically providing the integer number of 2 where we want to locate our robots. And similarly, we are also providing the integer number of 3 where we want to locate our bones. And similarly, we are placing our our dog, as an integer number of 1. So essentially what I'm doing is that I'm creating a 1D array where I have filled every position with 0, that is first every position is empty. Then I'm sequentially placing the robots and the bone and the player in our initial state of the game. And I have also created a flag that will act as whether the game has ended or not. That means whether the dog has come to this end position or it has accidentally stepped to this robot or any of the robot in the game. And this will act as a flag to check if the game has ended or not. So this is very simple setup for our game using 1D representation. And when we want to visualize the output, we can basically reshape this 1D array to a 2D array and replace 0 and 1 with these icons so that we can see where the dog is moving and where the robots are located and so on. Now, after that, we need to create, this is basically inside this init function where we want to initialize our game. And after that, we also need to create a reset method where if the game has ended, we need to reset the game to its initial position. And this is what essentially happening here. So this is basically resetting the game to the initial position where the dog will be, robot will be, and bone will be when the game ended and the next iteration starts. Now after that, we also create a new custom method called isSportLast, and this will basically act as if the dog has reached the end position. And if the dog has reached the end position, we will end the game and reset the game afterwards. Now the main function here in this dog logic class, dog adventure logic class, is this move dog method, and this will act as whether the move the dog has performed is a legal move or illegal move. Either the dog should get a penalty or reward, or it should end the game, and so forth. So basically what I'm doing here, so I haven't provided any code here, but I will share the link where the code is there, and you can look it afterwards if you like to go into the code. So for the sake of simplicity and to make it the slides more readable, I have avoided to include the actual code here. But whatever basically whatever happening here is that first I'm checking inside this function if the next position performed by this dog is the last position, and if so, we need to end the game by performing the flag to true, the game end flag to true. And if it is not the case, if the dog has performed some illegal move, that is, if the dog is in initial position and he wants to go left, that will be an illegal move because he will be outside the boundary of the game. And if the dog is at the end of the game but he wants to go even right, that will also be the outside of the boundary of the game. So this will be an illegal move. So if the dog has performed illegal move, he's also out of the game. And if the dog overstepped the robot, then he is also out of the game. And similarly, if the dog has overstepped the bone, he will collect the bone and get the reward. And similarly, if the dog just made a normal move going left or top or down or bottom, left or right, then go to the next state. So this is how we are moving the dog. We are checking if the position, if the move made by the dog is a good move or a bad move, and we are returning the flag or the response likewise. After that, this is basically the game environment. So after that, we create the TF agent environment that will use this newly created game environment so that we can train our agent. And to create a TF agent environment, basically we extend this Pi environment from TF agents.environment, and we include init function like before. But in this case, what we are doing is that we are specifying what is the specification for the action that the agent can perform, the observation specification, how the environment is, and what the actions the agent can perform. So let's go line by line. So first, with this action spec, whatever it is happening here is that we're basically saying the TF agent is that here is the action specification that the dog or our agent is allowed to perform. So this is the dog can perform from an array of specification, and it should be an array of integers, and the dog can perform from 0 action to maximum of 3 action. That is, if you go down to this line, you will see that if the dog has selected 0 position, then that is basically means the dog can go left. And if the dog has selected 1 position, then the dog can go right. If the 2, then down. If the 3, if up. So basically, we are mapping 0 to 3 integer to all this direction. And this action value basically mapping the direction to the next position the dog should be. And similarly, we are also specifying the observation or the environment for our game. So basically our environment is also a 1D array with 36 positions here, and it is also like consists of integer values, and it can contain from 0 value, which means the empty position, to maximum of 3 value, which means the bones. So this is the observation spec, this is the action spec, and this is how we are mapping each action from 0 to 3 to whether to go left, right, up, or down. And we are basically passing the previously created game environment, game logic object to this game internal variable like that. After that, we create a bunch of new methods, basically a reset method that will reset the game like earlier, but in this case, it will just call the earlier reset method that we created in the game logic. And similarly, if you want to see the game action spec and observation spec for some reason, we can also create a method that will return just that. After that, the main function here for this TF agent environment is this underscore step method, and this is where we are mapping every action, whether the action made is legal or illegal, or whether it should get a reward or penalty in this method. So basically what we are doing is that when the agent select certain action from 0 to 3, we map that 0 to 3 value to get the proper direction, either to go left to this position or right or top or down or whatever. And after we map that 0 to 3 position to a certain direction, we pass that new position to this move dog method that we created earlier in our game environment. And based on the position, based on the movement made by our dog, this move dog method will return certain response to this inside this method, and based on that response we will map whether if the move is illegal. If the move is illegal, then end the game with the penalty, and if the response is like it has found the robot, then end the game with penalty, and if the response is found the bone, then go to the next state and reward the agent with certain value like integer of 1. And if the game is a valid, then give certain small penalty like minus 0.3, so that we will train the agent to go faster in the next, to complete the game faster and go to the next transition. So basically whatever happening here is that we are mapping the action to the proper direction, and we are passing that direction to the move dog method that we earlier created, and based on the response we get from that move dog method, we are giving penalty or reward and making transition or ending the game based on that response. After that, we wrap our environment, we wrap our dog logic, dog adventure logic, and we create the environment. And this line of code is basically checking if everything inside our newly created environment is working properly. So in case we have some bad logic or bad in programming syntax or whatever, this validated by environment will check and return certain error if there is a error in our environment, and if not, then there will be no error. After that, we create two environments. One is train environment and one is evaluate environment. So basically we will train our agent using this train environment, and after we train our agent, we will evaluate the result of our agent using this evaluate environment. Now we have created a game logic where the dog can perform certain action or not. We have created a TF agent environment where this game logic can be called upon, and we can train the agent. Now let's go to the step where we can actually create the agent. So like I said, the agent that we are trying to create is a uses DQN network. So if you are already familiar with Keras or TensorFlow, you might know like Keras sequential API to create a model for different layers. Using TF agent, it's not. It's even simpler than that. So using TF agent, we can create a similar neural network, this DQN network, but without all this line of code like adding a layer or compiling it or training it. Basically, what we can do using TF agent is that we provide an array, a list where we want different layers to be. So in this case, what I'm saying is that we want 3 hidden layers, 3 fully connected layers with each having 32 neurons, 64 output neurons, and 128 output neurons. And using this kind of structure, we can create a DQN network, deep Q network using TF agent. So basically, we call Q network from TF agent networks, and we just pass our training environment, our action spec, and we are basically passing how much fully connected layer we want in our DQN network using this parameter. And creating a deep Q network is simple as that using TF agent. After that, we create the agent that uses that DQN network, and to do that, we are basically using this DQN agent, using this time, our training environment and the action spec on this environment and the Q network that we just created. And we can also pass Keras optimizer like ADAM optimizer or RMS optimizer in order to optimize our DQN neural network. And if you want to pass other hyperparameters, like in case of reinforcement learning, there are many hyperparameters like parameters to increase exploration or exploitation, and this kind of epsilon parameter and so forth. And we can all pass that kind of parameter as an argument here. And after that, we initialize our agent. So let's quickly recap. So what we have done so far is that we have created a game logic, we have created our TF agent environment, we have created DQN network using TF agent, and we have also created DQN agent itself that will use that neural network. Now, let's create a memory where all these different past actions and states and observation will be stored, and based on that memory, our agent can train from. So this memory is called, like I said, replay buffer, and this is basically nothing but a storage memory where all this past action the agent has previously performed will be stored, and the agent will basically call all this past observation from this memory and train itself using this memory. So to create this replay buffer, like in the diagram earlier, it's very simple. We just call this replay buffer with TF uniform replay buffer. And one thing you need to understand while creating this memory is that we want this memory to be as big as possible so that it can store as much histories or observation as much as possible. So in this case, maximum length is 1 million. And you can also tweak this value to a smaller or larger one, but based on the memory available in your device, you need to change that. So this is how we create a memory, a replay buffer using TF agent. And you might have noticed this something called observer. So observer is nothing but a function that will allow us to add all this past observation, this state to our memory. So from this replay buffer that we newly created, replay buffer that add batch, we are basically saying is that when we perform our agent on our environment, and when we collect this past action and state, we basically use this observer, this function, add batch function, to store to our memory. And this is as simple as that. After that, let's add some training metrics so that it will help while training our agent and help us give some idea whether our agent is performing good or bad or whatever. So there are two metrics basically in this case we are using. One is average return metric and another is average episode metric. So basically what happening here is that with average return metric, what we are calculating is that in one episode, what is the maximum reward it can get in one iteration, in one episode. So basically with this average return metric, what we are saying is that if we perform like 100 iteration, and in one iteration there could be like multiple episode, and what is the average reward that we can collect in each iteration. So this is basically performing if our agent can perform better or better based on the reward that it has collected. So basically average return metric will collect the average reward in each iteration that is performed. And similarly, average episode length metric means that how much it has taken, how much steps it can take to end one episode. So one thing that you need to understand here is that an agent can perform one step or one action at a time in one step, and in one episode there could be multiple steps, and in one iteration there could be multiple episodes. So basically this is what is recording is that in one episode how much steps it can perform before the game is over or the game is complete. So using these two metrics we can briefly we can get the idea of how well the agent is performing. Basically if the reward is high, it's good. Basically if the average return metric is high, it's good. But we want our average episode length metric to be somewhere in between, not too low and not too high. So and the next step is create drivers that will actually help our agent to perform action on our environment, and while doing so collect all these states and observation to our replay buffer, the memory. So to create this driver that will help our agent to perform on our environment, it's very simple as that. With this line of code we are basically creating a dynamic step driver that will take a particular number of steps using our agent, and while doing so it will use this replay buffer observer that will collect every trajectory, every observation to this replay buffer, this memory. So and after that before we train our agent using this replay buffer, what we need to do is that we need to first collect some initial data, initial memory to this replay buffer. And to do that, what we are doing basically in this line of code is that we are creating a random agent that will take random action from 0 to 3, and basically we are recording that action and the states that that we get from this random action, and recording that to our memory, so that when we actually start training our agent, we can start to train our agent from this action performed by this random agent first. And eventually our agent can get better and the action performed will be better, and the replay buffer will also collect some good actions and the observation later on. So basically we are providing a initial seed value, initial seed memory or data to our replay buffer before we actually start the training process using this line of code. And to get the agent, this to get a trajectory or the stairs to train our agent from this replay buffer, what we can do is that we need to provide this replay buffer as a data set, that is TF data format. So to do that, basically in one line of code, what we are saying is that basically get this replay buffer as a data set using TF data set, and get the sample size of 64 and number of steps to be 2, because 2 steps leads to 1 trajectory, that is earlier state and the next state. And basically we are collect this trajectory based off sample batch size of 64. So what happening here is that when we collect some initial data in this replay buffer, we are collecting this data as a form of TF data set and passing that to our agent to train the agent itself. And we train the agent using the trajectory collected in the replay buffer using this dataset method. And in this case, in this example, I have avoided to include the actual screenshot for the training code, which I will show you later on. But just understand that in this step, in this training step, I have trained the agent using the trajectory collected in that replay buffer, and I have trained that agent for 150,000 iterations. And after that, we will see, while training this our agent for 150,000 iterations, the agent gradually performs to go better. So this is a very highly noisy graph that we've seen. We see that it's not an ideal graph, because if we are measuring our performance of our agent in the terms of average return, it's with like a single line to go up and up and up. This will be the perfect graph, but in this case it is not, because it's very unstable and very challenging to train a DQN agent using just a random actions in the past. So this is very highly training. But on the good side, as you can see here, while training our agent for 150 iteration, it gradually tries to learn, and it is actually learning and performing better, because the reward is at the initial position from 0 iteration to, like, let's say 60,000 iteration. The reward is kind of like a 0. You know, there was not much reward, the average reward. But as you can see, after 60,000 iteration, the reward gradually increases, and the agent has actually learned to perform better, you know, in the later iteration. And similarly, as you can see, in case of average episode length, the length of the average episode is also increased, and it's not too high and it's not too low, it's somewhere in between. And this is a good scenario. Now let's evaluate our agent, this newly trained agent, and see how well it will perform in our evaluate environment. So let's evaluate and visualize the steps taken by our agent in this eval environment. Okay, let's see. So when we run our agent for one episode, and to take multiple steps in that episode, we will see in while evaluating that it takes our agent total of 14 steps to complete the game. And we can see at the end our agent has learned to complete the game by getting to this X position. And we can also see that the total reward that he gets is 12.6, which is bigger compared to the earlier iteration. So as you can see, in the game, our agent has learned to avoid the robots while taking all these steps, and it has also collected, let's say, we have total of 1, 2, 3, 4, 5, 6, 7 bones. It has collected all the bone except this 2 bones. So it is a good one actually. So it has managed to collect as much bones as possible. It has also managed to avoid overstepping the robots, and it has managed to complete the game by reaching to the X mark. So in this way, we can train our TF agent, our DQN agent using TF agent framework. So let me go through the actual code that I have used to train this agent. So for the sake of simplicity, I have avoided putting the actual code in here, but I will share the link at the end of this session, so where you can look at it. So if you go to this code, which I will share in a while, this is actually what I'm doing to train our agent. So let me just go up and show you the code. So as you can see, this is the actual notebook environment that I have used to train this agent. So what I have done here is that I have imported all the required libraries that I need to perform this TF agent and training. I have created the game logic, which I have showed you earlier. Yeah, this is basically the game of the environment, and as you can see in a move method, it is basically checking if the sport is last position, then end the game and return with the response of game complete. And similarly, if the move made by our dog is illegal position, then return with a illegal move response and end the game. And similarly, if our dog overstepped the robot, which is the number 2, then say response with found robot response and end the environment. And similarly, we can create the game logic like that. And similarly, for TF agent environment, what we are doing, like in the case of slide, we have created the action spec, observation spec. We have created a mapping for our action taken by our agent to the direction where he wants to go next. And similarly, what we have done here is that basically we have taken the action, either it's 0 or 1 or 2 or 3, then we have mapped that action to a response, whether it's go left or right or down or up, and we have passed that position to this move dog method and get the response. And if the response is a game complete, then return. If the response is game complete, then terminate the game with a maximum reward of 10, which means the game has successfully completed. And if the response is illegal move, then terminate the game with a penalty of minus 0.3. And if the dog has found the robot, then minus 0.3 and terminate the game. And similarly, if he has found bone, then give the reward and transition to the next state. And similarly, if the move is just a valid move, give the penalty of minus 0.3 and continue to the next state. And similarly, like in the case of slide, I have initialized the environment, the DQN agent with proper optimizer and all the hyperparameters to create our agent. We have created our replay buffer, our metrics, the driver that will actually run our agent to this environment to collect all this observation. And we have collected some initial observation as a data set to train our agent on before performing the agent actually on the environment. We have created the replay buffer as a data set. And this is the code where we'll train our agent. So basically, what you need to see here is that we have created the data set from this one. So replay buffer as data set will create this data set. And basically, we are iterating over this data set. And in each iteration, we'll get trajectory for as a batch of each batch will have number of trajectories here. So we are just basically one batch of trajectory, and we are training our agent as agent to train and training our agent on these trajectories. And we are basically recording the loss. We are basically recording the training metric that we initialized earlier. So when we train our agent for 150,000 iteration, we will see that this is the result in each iteration that we'll get. So by the end of this iteration, by the end of 150,000 iteration, let's see, let's go down. We will see that the average return is 13.18 and the average episode length is 16. So in one episode, in average, the dog takes about 16 steps to complete the game. And in one episode, our dog has managed to collect the average reward of 13.18. And similarly, we can plot the metrics and see the result. And here, to visualize our actions the agent has performed, what we have done is that we have reshaped our one-dimensional environment to a two-dimensional one with 6x6 matrix. And we have replaced 1 with the dog icon, 2 with the robot icon, 3 with the bone icon, and 0 with this blank space icon. And we have basically run this one episode of visualization on our evaluation environment, and we have seen that on step 0, our dog is in our initial position. In step 1, the dog manages to go right, and in step 2, the dog manages to go up and collect the dog with collect a bone with which will get the reward of 1. And similarly, using this method, the dog has managed to complete the whole game in 14 steps here with a total reward of 12.6. So in this way, you can actually train your agent using TF agents. And if you want to learn more about this in detail, much detail than I have just talked to you, you can go to this blog called Train Your Dog Using TF Agent on Medium, and you can read all about it here. In this blog post, I have explained every step and everything here. And interestingly, I have also created a second part for this blog called Train Your Dog Using TF Agents 2, Revenge of Kiko, where our dog is now not alone. Now our dog has a friend, a cat, which will help our dog to complete the game faster and collect more reward for him. And here's one special thing that I have done in the second part of the blog. I have managed to add one more action to our agent. That is, so far our agent has trained to avoid the robot and complete the game. But now in the second part, our agent has also managed to learn a move attack, or attack move, where he can actually attack the robots. And he doesn't need to avoid the robot. He can actually attack the robot and get more reward and collect as much bone as possible and finish the game. So as you can see, this is a bit complex than our existing scenario, where there are two players controlled by a single DQN agent. And the agent has also learned to perform not only movement and avoid the robot, but also attack the robot by both these two of the agents. So this is pretty interesting, and if you want to learn about it, you can learn about this in the blog as well. So I have written a blog about that as well. You can learn about it as well. And with that, if you want to learn more about this TF agent, then you can go to tensorflow.org/agents, and there is everything that you need to know about TF agents, how you can create your custom environment, train a reinforcement learning algorithm using DQN or other kind of algorithm in reinforcement learning. And if you want to learn a bit more in detail, then you can buy this book called Hands-on Machine Learning with Scikit-learn, Keras, and TensorFlow. And basically in chapter 18, there is a reinforcement learning chapter where the author has talked about the TF agents and how we can go about train our agents using TF agent. And if you are interested in learning reinforcement learning and deep reinforcement learning in general, you can take this course from YouTube by DeepMind, where there is much of a theory behind reinforcement learning and deep reinforcement learning. And you can also get this book for free called Reinforcement Learning by Richard Sutton and Andrew Barto. And this is like a Bible for reinforcement learning. You can learn everything about reinforcement learning from this book. And with that, thank you so much. I hope you enjoyed this session, and thank you so much for allowing me to speak and share this knowledge among you.
Okay, thanks, Kshitiz. Thank you very much, and I think that's a great presentation, and thanks you again. Now I think I will understand what is reinforced learning. Okay, thank you very much. So now we're beginning question and answer, and I will using Chinese to say that. Okay， 那么很感谢那个Kshitiz 做的这个就是分享哈，然后现在就是大家有什么问题可以提出来，我们尽量能够翻译成就是英文，让就是 Kshitiz 给大家做一个就是回答。
Kshitiz, I have a question.
Okay, please.
In the dog in the park in this game, and I see you what is the sneak attack in this game?
What is the sneak attack?
Yes.
Okay. So let me share you my screen and show you what that means. So, okay. So, as you can see the screen. Okay. So in this game, let me show you the screenshot here. Let me see if I have, yeah. So sneak attack is basically the diagonal movement from one position to another position. So in this case, our cat is here. So if he moves this diagonal position, whether this left or right or up or down, this diagonal movement is called sneak attack. So when the agent performs this snake attack, he will not get penalty. He will actually kill the robot and get the reward. So I have added that extra action to increase the reward, and so that our agent can learn few more moves instead of just moving around in the park.
Oh, okay, thank you. Another question. In the dog in the park, I see you didn't finish. If response is found robot, you will get a penalty, and if the response is found bone, you will get a reward. And
yes.
And if the response is valid move, you will give a small penalty and translation. I have a question about this. How do you think why the response is valid move, you give a small penalty and transaction? Why?
Okay. So you mean why the valid move has penalty, right?
Yes.
Okay. So the biggest objective for our dog, instead of just collecting the bone or attacking, or hiding from the robot, the biggest objective is to complete the game, and to complete the game as fast as possible. So to do that, every steps he makes, if he gets a penalty, it will force him to move in a direction that will actually complete the game faster. And to do that, I have given penalty to every action. If you don't want how long it takes for an agent to complete the game, then maybe you can remove the penalty, and that it might take a longer to complete the game. And the agent can roam around and collect every bone and then complete the game. But what I have done here is that complete the game as soon as fast as possible without making unnecessary move. But at the same time, if he manages to collect as much bone as possible, he will also get some reward. So that is why I have given penalty in every step, so that it will force the agent to complete the game faster.
Okay, thank you very much.
Okay, thanks, Kshitiz. Any other question? 请问其他朋友还有就是问题吗？Okay, Kshitiz, I have a question, and I see you do some job in IBM, and you get the project core code in IBM, in fact, and you get awards. Yeah. So I want to if it's possible, could you just introduce this project for us, and how do this project, and there is some AI or TensorFlow program you use in this project or not?
Oh, okay. So you mean the call for code project that I did in 2018,
yeah.
Right? Okay.
Yeah.
Okay. So this project is called PD3R, which is basically means post-disaster rapid response retrofitting. So what I have done with this project is that during that time, during 2015, Nepal faced a biggest earthquake. It was like a bigger magnitude, and a lot of the houses in rural part of Nepal were damaged. And what I have done basically in this project is I have created an image classifier that will take images of the broken houses in a rural part of Nepal, and using that images of the broken houses in rural part of Nepal, I have created neural network that will predict whether that house can be performed structural retrofitting on it or not. So basically, I have done this classification based on the image of the house, whether that house can be repaired using retrofitting or not. And I have built with this organization called Build Change to this application, this Android application that will use this deep learning model that will take 4 images of the 4 side of the house, and it will run prediction on each images and tell the house owner whether the house can be perform retrofitting or not. And that will save the time and money of the engineer to come from the city area of Nepal to the rural part of Nepal and measure the house by every inch. So this is like a basic, first level of screening for the house owner to get to know whether that house can be repaired using retrofitting or not. And if that house can be repaired using retrofitting, then he can call the engineer and come for him to get all the measurement and actually repair the house.
Okay. And so I want to know. I'm very interested for this project. I want to know you use technology for make sure the house can be used or not, is GPS or some other technology. What technology?
We didn't go to that kind of sophistication right now. During that time, it was more about the competition and how we can faster prototype a result. So what we have done is that we have come to a hypothesis back then. So here is that thing. So we have collaborated with a organization called Build Change, and this Build Change organization had a lot of structural engineers and civil engineers that work on this retrofitting domain. And one of the engineers, the senior engineer there, he suggested that most of the time while evaluating certain house for retrofitting, what they do is that they quickly glance over the house and see if there are like major holes or cracks in the wall, and there are major openings in the wall of the house. And if there are like big holes or big crack in the wall of the many walls of the house, then that house cannot be repaired. It should be very less. And basically the space between the windows and between these two windows is bigger and the crack is smaller, then the house can be, even we can estimate that house can be repaired somehow. Of course, there will be an actual estimation. To get the actual estimation, you need to measure the house inch by inch and do everything manually. But to get the higher level estimation and to save the time, you can see from outside and get the idea whether that house can be repaired or not, or whether that house is severely damaged or not. And using that idea, what we have done is we have basically trained our neural network on simple images of these broken houses, and we have labeled those images using the engineers they have in that organization. So they will basically look at the images of the houses, and they will label the houses if they can be repaired or not, and based on that images and that label data set, we have trained our neural network. So it's just some image classifier that will do first level of screening. It is not that rock solid, perfect model, but it will give the house owner idea whether he can expect to repair his house using retrofitting or not.
Okay, it's very interesting. Thank you very much. And if it's possible, could you just send me some documents or information about this project you do, and after that we will discuss it. Okay?
Okay, sure, thank you.
Okay. There's any other questions? Hi guys. 大家还有其他问题吗？ Okay. So wait. 小蔡，喂，小蔡，你还想做一些补充吗？现在？
没有了，我这边没有。
Okay. I think thanks Kshitiz, and now I think this presentation have this event we were finished. Thank you very much, and I wish next time we were together and share your presentation together again. Okay. Thank you very
Yeah,
much.
sure. Thank you so much. I'm looking forward to that. And have a great
thank
day.
you,
Stay
Kshitiz.
safe, and thank you so much for having me. Goodbye,
Thank
everyone.
you. Goodbye. Goodbye, kids.